Now we are finished with chapter 1, and we move on to the practice problems for chapter 1. So 1.10 is our very first one. Thankfully, it is a relatively trivial problem. Consider the first 25 digits in the decimal expansion of pi. So we take 3.14159, so on, all the way up to 25 digits, and we put them all sort of in a list. And the first part asks us, if you selected one number at random from this set, what are the probabilities of getting each of the 10 digits? And hopefully this is sort of a trivial exercise for you. We can just sort of count them effectively. And I've already done that here just to make our lives a little bit easier. So this is the respective digit from 0 to 9, and then the number of times they appear, and as a result, their respective probability, which is just the number of times they appear, divided by the total number being 25. So let's move straight on to part B. And part B, hopefully, is also very easy. What is the most probable digit, first off? Well, if we look at sort of the number of times each digit appears, we see that 3 appears 5 times, which is more often than any other digit. So as a result, for the first part of B, let's say I, we're going to say that the most probable digit is, in fact, 3, because it appears 5 times, which is more often than any of the other digits. Part 2, what is the median digit? And first off, what we see is that there are 25 digits total, so evidently we want the middle digit value. If we take 25 and divide it by 2, we get 12.5, so that means we're looking for the 13th digit, because there are exactly 12 digits below and exactly 12 digits above. We can ignore 0, because 0 doesn't appear in the 25-digit expansion, so starting from 1, we can just count up. So 1 appears twice, 2 appears 3 times, so 2 plus 3 is 5, 3 appears 5 times, add that on, that becomes 10. So evidently 12 comes up at digit number 4. At 4, we get the 12th digit that appears. The 13th digit is the one we want, which happens to also be 4. So our median is in fact 4. So we say that because there are exactly 12 digits that appear below 4 and exactly 12 that appear above 4. And finally, we want the average value. And we sort of already know the formula for finding the average. We sort of just take the sum of all the respective digits and divide by the total number of digits that appear. So if we do that, I'm just going to save time and just give the answer. It gets calculated exactly as 4.72. And I'm not going to sort of elaborate on this anymore, because we've already gone over how to actually calculate the average plenty of times in the previous section. I think the first section or the second section when we go over probability. It's the third section where we go over probability. So if you're not familiar with how to calculate the average, please look at that one, section 1.3, which is the probability review, but statistics review in general. And then we go on to part C, which is to find the standard deviation for this distribution. And we already know what the formula is. We know that the standard deviation is equal to the square root of the expectation value of whatever we're looking for, A squared, subtracted by the expectation value of A itself, and then squared. And once we write this out, well, we already know that the expectation value of A itself is just 4.72. So this, in fact, equals, and we can sort of calculate this as well. The expectation value of A squared, or the digit squared, is just a matter of replacing each digit with their square value and recalculating the average all over again. So 1 remains as 1, 2 becomes 4, 3 becomes 9, and so on. And if we brute force that, that just becomes 28.4. And I'm just going to give that for the sake of saving time, not wasted on doing sort of useless menial calculations. And we want to subtract that by 4.72 squared, because that is our average that we calculated in B part 3. And if we do this all the way, this becomes 2.474. And with that, we have finished 1.10.